Hi guys, Shouvik here. Welcome back to our channel. So today we will back with another questions and let's get started. Yes, so on today's questions we have put marbles in bags. So now first let's try to understand the problem statement. So in these questions we have k bags and you are given a zero index integer array weights where weights of I is the weight of the ith marble and you are also given an integer k. So I think it's very straightforward English. So what they have given a weight array and weights of I is the weight of the ith marble placed in the weights array, and they have given k bags to us. And now we have to divide the marble into the k bags according to the following rules. So the first rules is no bag is empty. So we have to put at least one marble to to each k bags. And if the ith marble and the jth marbles are in a bag, then all the marbles with an index between I and j indices should also be on the same bag. So on the weights array, if you are choosing from, if you are placing first marbles which is at index 0 and index 2 marble, that is 0 1 2, I'm considering it as a 0 based, and index 2 marble that is of 5 or 8 marbles, then 3 marbles is automatically go to back where you are putting index 0 marble and index 5 marble. So you can select a chunk, of weights, you can select a chunk from your weights array and put them to your bag, and if a bag consists all the marbles with an index from I to j inclusive, then the cost of the bag is weight I and weight j. So if you are putting all the marbles from 0 to 5, 0 to 2, 0 to index 2, from index 0 to 0 1 2, that is 1 3 5, then the cost is going to be the weight of the first marbles and weight of the last marbles, the chunks that you have selected. Now the score after distributing the marbles is the sum of the cost of all the k bags, I think it's very straightforward. And now, like this way, when you put all the marbles to the k bags, then the final score that you got, that is the sum of all the valid arrangements. And what is a valid arrangements? This is a valid arrangement. So you can select the chunks from index I to j and you can put them to a particular bag, and that particular bag is contribute to your answer to the weight of the first marbles and weight of the last marbles. That sum, and your total score is the all the bag sums, and each bag sums we just mentioned. And what you have to finally return? You have to finally return the difference between the maximum and the minimum scores among the marble distribution. The difference between the maximum and the minimum scores among the marble distribution. I think the question is very straightforward, and if you can iterate to one of the test cases, then you can obviously get the gist. So what you can do, you have two bags, so you can split your weights into two chunks. So let's suppose I split from here. So first bag have only single marble and second bag have rest three. So the results in the minimum score is, so this is like this distribution is giving you the minimal score. And what is it? So on first bag we have only single marble. So for single marble, what is the first? It's so we can consider 1. And what is the last? Itself is, so we can consider another 1. So on the first bag, contribution is 1 plus 1. And for the second bag, what is the first marble? It's 3. What is the last marble? It's 1. So what is the contribution? 3 plus 1. And what is the total score? Total score of such split is first bag contribution, second bag contribution. So like this, if you have k bags, so you have to do the sum of till k. So now here we have 2 bags, so we did first bag's contribution plus second bag contribution. So on that case we have 6. So that is the minimum score we can achieve. And like this way, if you can split here, so first bag has 1 3, second bag has 5 1. The results of the maximum score is first bag contribution is 1 plus 3, second bag is 5 plus 1, and total score is first bag plus second bag is 10. And we return the difference. What is the maximal we have achieved? It's 10. What is the minimal we have achieved? It's 6. So the difference is 10 minus 6. So the difference is 10 minus 6. It's as simple as that. And now here on this arrangement, you can see like we have to split them in 2 bags, and you know no bag is empty, so you can't put all the two bags to a single bag. You can't. So you have to put at least one marbles to each bag. So on that case, the only distribution possible is first bag has 1, second bag has 3. Since both the maximal and minimal score are same, we can return a 0 altogether. The difference is 0. I think guys, the question is very straightforward, but the question is tagged at hard. So basically they are if a particular question is tagged as hard, na, so there should be some like eagle eye you have to put to basically figure out your most optimal solutions. And if you can take a look on your constant can go to a 10 to the power 5. So one thing, so we are definitely can sure that if I can go to our favorite OneNote, so if I can take some number, so let's suppose I have some number I. Am I able to write? No, I am not. Yeah, so right now, yes. So let's suppose I have I, then comma, then J, then K, I, J, K, L, M, N. Let's suppose I have this all I, J, K, L, M. N, right? So one thing I can surely state for this particular question. I have some choice. Either I can do a partition. So where I can make the partitions. Either I can make a partition here, or I can not. I can make a partition. Yes, I can make a partition. There can be cases, right? So what happens to this pane? Or I can't, right? So either I can make a partition. So if it is yes or no, so there can be two cases. There are two cases. So either I am able to make a partitions, or I am not. So like this way we have choices. So that is one hint that you can go for recursion. So you can write a standard recursive functions altogether. So for every index I, you have choices. So if you make partition, then what is the contribution? You should know these following things. Last partition index, you have to know. And so that's things. So I think if I know this, then I should be good. So I have to know where I have made the last partitions. So there can be another pointer which is basically pointing to last partition index, right? Last partition index. So and we have the k factor, we have this k factor, we have our k factor. So if I can make a partition, then what is the contributions to these particular segments? If I can write it here, so here can be I have made a partitions, let's suppose at 1th index, so I have start from 2th index. So I can say my here contribution is nothing but my weights array of last partition plus 1, last partition index plus 1, plus of if I want to make a partition current index, so my weights of current index. So that is my here, and so on my next functions call. So I can make a call, I can store this to my answer, and I can make. So if I am doing a partition here, so here is going to be added to my answer, and I am calling my helper, to for sure I plus 1, and my last partition index is going to the current I, because I made a partition here, and my k factor is going to be decreased. My k factor is going to be decreased to k minus 1. And so that is one thing. And so if I can mark it answer 1, another things can be possible if I am not making a partition here. So nothing is going to be added from my answer, and I am going to standard I plus 1. What is the last partition index we have at? We will pass as it is. And my k factor is also same. So that's it. And like this way we can return. If I, so one helper we can run for max, and one helper we can run for min. So if let's suppose we are running max helper, so we can return on max of answer 1 and answer 2. Either of them we can return. So that is the done partition. That is the done partition case, and that is the non-done partition case. Right? But now I am not going to write the base case and everything at all, because that is not the optimal solutions. Because how many parameters are changing here? We have one parameter is this, another parameter this, and another parameter is this. So how many parameters changing? 3 parameters changing. 3 params change. So, and what is the size of each param? I can go to as big as n, Another factor is last index. Last index also can go to as big as n. And the third thing is my k. And if you can take a look to your k factor, k also can grow as big as n. K also can grow as big as n. So if I can combine this and try to apply a dp, top of that, this is going to be take a n cube. So that is going to be a kind of n cube. So I'm not sure. Yes. So that is a kind of n cube solution. I can write it something like this, n cube. So that is not. So that is the time complexity for this particular process. So can an n cube is accepted? Nope. Because our weights can grow as big as 10 to the power 5. So 10 to the power 5 into 10 to the power 5 into 10 to the power 5 is going to be 10 to the power 15, which is a direct TLE. Now I think so. You have done your recursion and you have tried with DP also, and that also is giving you a what? That also giving you a things which is also in the range of n cube, So now I think you have to think a little bit more. And trust me guys, like when you done your pen and paper work, so that's only you can identify this approach. So I have to say that is really a very organized way, organized way of problems they have set it here. So if you can write that for a big test case, when you write the entire things, how actually the points are going to contribute to answer. So what is actually is contributing to our answer? What is actually contributing to answer? If we have a subhead, what is actually going to contribute to your answer? So please first clarify yourselves with these questions. What is actually contributing to our answer? If we have a subhead, what is actually contributing to our answer? This terminal nodes, it's terminal points only, because here it is directly mentioned weights I and weights j. These two terminals are actually contributing to your answer, So if I can choose my terminal points, in a optimal way, then I think we should be good. Now how we can choose our terminal points in an optimal way. So first try to understand what is actually contributing to our answer. So I actually did a detailed pen and paper, and then only the actual solution is straight to my brain after like writing a very big test cases. So I am also giving you the same type of intuitions, how you can actually build your problem solving ability by writing the things, by writing various test cases, edge cases, and then only you can identify the most optimal solution. So let's suppose again write the same test case. If we have I j k, then I j k l m n o p, right? So let's suppose we have this. If I can make it a little bit smaller. So let's suppose we have to choose a bucket of we have came with a bucket of k equals to 3, right? K equals to 3. Right, k equals to 3. Let's suppose you came with a bucket of k equals to 3. Now I have to make them to put in the 3 buckets. So let's suppose I make a partition here at these particular points, and then let's suppose I made a partitions at these particular points, and I think I have done, right? So one partition has these 2 values, another partition has these 3 values, another partition, right? Another partition has these 3 values, and the last partition has this all. So the first partition's contribution is nothing but I plus j. The second partition's contribution is k plus m, and the last partition's contribution is n plus p. And what is your score? Just add plus in between. Yes. So what is then actually how you have built your score then? So that is actually nothing but your score, right? So that is your score. The entire thing is your score, right? So what is actually your score? Then, right? So your actual score is nothing but the terminal point sum. So here we have terminal points ij, here we have terminal points kn, here we have terminal points kp. So now if you can try to observe, now let's suppose put your eagle eye here. Control Z. It's not working. Why? Yes, it's working. So let's put your eagle eye. That is our eagle eye, right? Let's put your eagle eye here. So we have a eagle eye here, right? So what actually, or better I have to say, put your eagle eye here, where actually the plus has happened. We have an eagle eye set at here. We have our eagle eye set, right? Now what actually contributing to your answer? So rather than the terminal points, can I say the adjacent terminal points? Can I say these adjacent terminal points are contributing to our answer? Can I say yes, Shouvik, you are partially correct. This is also contributing to my answer. This is also contributing to my answer. And A, so here, so first partition is my this, second partition is my this, second partition is my this, and my third last partition is my this. So rather than concentrate on the partition terminal points, if I can consider adjacent backs terminal points, yes, that is also true. So one is this, another one is this. So these two are adjacent terminal points partition, right? And first one and the last one, is always going to be at, because they are always going to be the terminal state, right? They are always going to be terminal state. So if I can do the same things in another way, so let me do it. So let's suppose we again have I, J, K. Now I am taking smaller I, J, K, L, M. And let's suppose if I am doing a partition here, if and my K factor, let's suppose again as 3, my K factor, right? My K factor again as 3. I did a partition here, and let's suppose I did a partition at here. So I'm just giving you how this same things is going to be applicable for if you do single partition, single element partition. So then what you have? So your first partitions is going to be start from I plus I. That is your first back contribution. Your second back contribution is nothing but your J plus L, and your last back contribution is nothing but M plus M. Correct. With this arrangement. So again the same things. If rather than taking the terminal point contributions, if I consider the adjacent backs terminal point sum. So this one is 1, right? This one is 1, and if I consider this one is another, L plus M, this one is another, right? Not this M. So the first M till this, right? And again the first this guy, and the very last guy, this M, is always going to be my answer. So now I think who are actually solving this difficulty level of question, I think they got the gist what they are basically looking for. So if my K factor is equals to 3, how many adjacent elements, how many adjacent back terminal points we are looking? It's nothing but 2, right? So this is 1, and that is 1, and first and last is always going to be my answer. So for maximum score, what actually we have to maximize? This factor and the last factor is always constant. They are always going to be your answer. So what actually the internal K minus 1 partition, right? So for K equals to 3, you are able to choose terminal sum of 2, which two? These two, which we have already highlighted, these two. So now the problem boils down to we have to choose K minus 1 consecutive sum. We have to choose K minus 1 consecutive sum in the weights array, where it's maximum, So we have to choose K minus 1 consecutive sum in the given weights array. So what is actually remaining? So that is for maximum. That is, this formula is applicable for your max finding, and what formula is going to be applicable for your min finding? Same things, just replace this maximum with minimum. You have to choose K minus 1 elements, K minus consecutive sums which are minimum. So what else? I think we have solved the problem. And what actually data structure we can put? What data structure we can put? I think you should answer this question. What data structure? So if you have so what the problem boils down? You have an array A, B. Let's suppose A, B, C, D, C, D, E, and I am asking put all the adjacent. A plus B is 1. Another one, so this is one group, B plus C is another group, C plus D is another group, D plus E is another group. So all the consecutive, and first and last is always going to be your answer, that we have to. So and I am asking to choose K minus 1 out of them, K minus 1 out of them, which are maximum or which are minimum, right? So what else? What data structure we can choose to basically store first K minus 1 or k can be any arbitrary integer. First arbitrary integer max value. So out of let's suppose n, if I am asking to n minus 3 maximum values, which data structure you can choose? Yes, tell me. It's nothing but heap. It's nothing but heap, right? So let's suppose for to choose the maximum elements, we can go for a min heap. We can go with a min heap. We can go for a min heap. For maximum, we know we need a min heap. For minimum, we need a max heap. So let's understand one. You can vice versa you can understand the another one. So for maximum, why we can go for a min heap? So for maximum, why we can go for a min heap? So we know min heap basically storing min heap top giving you mean value, right? So I have the liberty to make a k-1 split. So I can choose k-1 consecutive, that we just proved. So no matter when I am iterating from I equals to 0 to n-1, or maybe n-2, and I am choosing an here variables, which is basically my weights of I plus weights of nothing but I plus 1, and when I am pushing them to my min heap, and I am always going to be pushed to my min heap, I am always going to push this to my min heap, right? And push it to my min heap, and I am checking what is the liberty, what is the size I can maintain. I can maintain a size of k-1. So that is the liberty I have. So if at any particular time my min heap is going to be more than my size, I will pop from my min heap. Can you pop yourself? What is the elements it is going to be pop? It is popping out the minimum one. It is going to be pop out the minimum one. And if I think you should be aware of this algo, but I am giving you the gist, because if by any case if you are not able, so I am basically building the intuitions why min heap basically giving you to store the maximum k consecutive elements to maximum k. So like this way, when the size is more than my size, and we know our size is k-1 is more than my size, we are popping, right? And like this way we are popped all smaller elements, which are we are able to pop all the smaller elements in our consecutive sum, and what else? And so now we are maintaining a min heap. Which stores which has a size of not able to write here, which has a size of k-1, and I have already popped. I have maintained the size. How I have maintained the size? By popping the elements. So I have popped all the smaller elements. I have already thrown. I have which thrown? Minimum or smaller. I have already thrown from my min heap. Already throw out. So now what actually the k-1 elements we have in our min heap, that is actually the maximum k elements, maximum consecutive sum k elements we have set in our min heap. All the k-1 consecutive sums which are the maximum are stored in our min heap, and you have to do the just reverse for your minimum calculation to your minimum calculation. So we have used min heap for our max code calculations. You can use max heap to your min calculation. So in Python there is no max heap exists, so you can use your min heap. How you can use your min heap to a max heap, so that it is going to be act as a min heap, just pushing a negative of the particular elements, just a negative of that particular elements. Then on that case your min heap is going to be work as a max heap. It's as simple as that, guys. It's as simple as that. So now let's go to the code iterations. You can get the entire gist of how we have implemented. So the main gist of this particular problems is, rather than doing a particular backs terminal sum, you can do that adjacent backs first and last sum, so that is actually the challenging part to identify. And if you are able to identify, then rest is, it's a cakewalk for sure. So now we have initialized our n with weights, and we can choose. We know it is nothing but k-1. So k-1, that is the size. So how many we can choose? Can choose. So that is this k-1, and we have initialized our min heap and max heap with empty, and we know mean answer and max answer is, no matter which answer we are calculating, our first and last is always going to be added. So we have added both mean answer and max answer with the first and last of the weights array they have given to us. And what is the current min heap size is 0, what is the current max heap size is 0, and now we are iterating to I from n minus 1, from I to n minus 1, less than n minus 1, that is of n minus 2, because we need the adjacent and we will do a I plus 1, and so maybe on that case if we are going to iterate on n minus 1, then on that case we are going to an index out of 1. So I think it's very standard. So we are iterating to n minus 2, from 0 to n minus 2, and we are doing what is the here contribution to this particular index, its own and its adjacent, its own and its right adjacent. So we do its particular here and we are pushing to our both heap. So for min heap we are pushing as it is, and for max heap we know in Python there is no max heap. How we can use our min heap as a max heap? We will push a negative of that. We are pushing a negative of that, and we are doing our min heap size plus 1 and max heap size plus 1, as simple as that. And now if at any particular points, if my min heap size is more than my can choose, we will do a heap pop from my min heap. And same things, if at a particular point, if my max heap size is more than my can choose, I will pop a particular value from my max heap, and like this way we have all the k elements which are all the k consecutive, not k minus 1, or I more specifically I have to say can choose elements, which is nothing but our k minus 1 elements is stored. All the maximums are stored in our min heap, and all the minimums are storing in our max heap. But for max heap we have pushed to negative, and we will pop, we will again do a negative of negative, so that we will get the actual value. So we'll multiply it with minus 1, so that we have pushed with a negative. When we are popping, when we are doing our operation, then also we are want to work with the actual value. What is the actual value? That is what max heap is giving us. Just do a negation of that, just do a minus 1 multiplication of that number. So that's why we are going to get with the actual value which we have pushed. So now we have our min heap and we have our max heap, and now we will iterating our can choose. So that many elements we are able to choose. We have pushed to our min heap and we have pushed to our max heap, and for max answer from which heap we have to push our answer, that is from min heap, that we are like very start we are stating. And for min answer, which heap we have to choose our max heap, and we are going to multiply our answer to minus 1, because on max heap we want to use, because we know on Python there is no max heap concept. The min heap we are using as a max heap, so we have pushed as a negative here, so we want to get the original value by doing a minus 1. And also we are doing can choose minus equals to 1, and finally we have our max answer ready, we have our min answer ready, and finally we doing a max answer minus min answer, which they have asked for. Yeah guys, so the question is as simple as that. So the main trick, you rather than considering a particular back terminal, you can consider the adjacent back terminal sum. So that's the trick. And how we are able to identify that is very straightforward. Just writing a very long test case, and we are able to identify these things. So this is actually the core brain I have to say to this particular problem. Rather than the current back terminal, we can do a adjacent back terminal, So if you are not able to understand, please go to this particular explanation sections of this video. Please go to the iterations, please go to like couple of iterations or thrice or four times iterations, then you will obviously get a gist of this one note expansion. So that's all about this particular problem. And now quickly discuss about the time and space complexity. I think you guys is already written your own time and space complexity, because we all know what is the TC and SC for if we are using a heap based solutions. So pushing a heap, you guys know a log n, and if for n elements we are pushing and popping, so that is obviously going to be taking a n log n factors for sure, and we are doing for 2 heap, so that is a kind of 2n log n, as we are using 2 heaps. This particular things is going to be taking for sure 2n log n, more than 2n log n, and if the size is more than my k, then also we are popping also, so in particular one operations we are pushing to both the heaps and we are popping from both the heaps, and each heaps is going to be taking n log n, and so that can be, you can say a 4n log n, but that is not correct. So you can write it in 2n log n, because it is only going to be executed when our size is more, when your mean heap size is more than your can choose. But yeah, like you can explain to your interviewer, and if he considered it as a 4n log n, then also we should be good, because 4 is also a constant factor. So our ultimate solution is n log n only, and then for choosing a can choose is going to be taking another times of k minus 1, another time of we are iterating on can choose, and we are also doing heap pop, and heap pop again doing a log n factor. So here also we have to consider k log, and what is the size of each heaps? I have to say it is of k minus 1. So rather than writing it as a, so it is a n log k for sure, because we are maintaining a size of k minus 1, or more specifically you can write these things, because your heap size can grow as big as k minus 1. So into we are iterating for sure, and for every things we are doing n log k minus 1, and here also like k log k minus 1, because can choose can grow as big as k minus 1. or it should be k minus 1 only, k minus 1 log k minus 1. So that is the time complexity. I have to say exact time complexity if you are considering everything, every iterations, every heap push, every heap pops. So that is the time complexity. And on the space part, we are using two heaps. So each heaps can grow as big of k minus 1. So you can consider it is a in log 2 log. Tell me guys, 2 log k minus 1, 2 log k minus 1. So that is the time and space complexity for this particular solutions, that particular problem statement that I am able to figure out. And I think it is the most optimal time and space complexity, because our submissions is more than 95% faster mostly, mostly as I saw. Yeah, so that's it guys, that's it for today. And if you are able to, so I have to say that is like identify this particular tricks is quite satisfactory for me. And if you are able to understand till this point, I know what you have to do. So please do subscribe to our channel. Please turn on the notification, so that when we are going to be live with our next video, you will get the very early notification for this particular video. So that's it guys, that's it for today. Bye, see you.